In this video, I will be explaining the Heun's method, which is a numerical method to solve ordinary differential equations. So Heun's method is a slight modification of Euler's method that we discussed in a previous video. So recall from the previous two videos that we can express the numerical solution to an ordinary differential equation in this general iterative form, where your value of y, I plus 1, is going to be based on is yi plus phi times h, where phi is an estimate of the slope and h is the step size. So recall for Euler's method that the estimate of the slope was equal to the slope at the start of the interval. And Heun's method improves, or tries to improve, the estimate of the slope by instead determining the derivative at 2 points on the interval, namely the beginning and the end point, and then averaging them out to obtain an average slope over the interval. So the idea behind Heun's method is sort of presented in these figures. You have the interval that ranges from xi to xi plus 1, and we have a known value of yi at xi. We use that to estimate the slope at this point xi. Using that slope estimate, we can make an estimation of the value of y at the point xi plus 1, and then we estimate the slope at that point again, we average them out, and then we obtain an average slope over the interval. So now let us derive a general expression for Heun's method. So again, consider this ordinary differential equation in this form. I'll write it down here again. Not so thick. dy over dx is equal to some known function of x and y. Now we can integrate this expression with respect to dx to get this. We can get rid of these dx, and because we integrate over this interval, we can create a definite integral from yi to yi plus 1 of di, which is going to be equal to this definite integral from xi to xi plus 1 of f of x and y plus dx. So this integral on the left hand side we can easily evaluate. It's just going to be equal to yi plus 1 minus yi. And now we want to also evaluate the integral on the right hand side. And for that we will use a numerical method that we discussed in the numerical integration videos. Namely, we will use the trapezoidal method of numerical integration. So recall that the expression for the trapezoidal method was this: f of evaluated at xi and yi minus f at xi plus 1 and yi plus 1 divided by 2 times this step size h. And because we use the trapezoidal method, the truncation error is going to be equal to the error of the trapezoidal method as well. And recall that for a single application of the trapezoidal method, this error depended on h to the third. So we also have this big O of h to the third as well. So we obtain this expression for the Heun's method, and this is the final expression for this method. So, as I explained, Heun's method is second order accurate because the local truncation error depends on h to the third, and that local truncation error comes directly from the use of the trapezoidal rule. Now we can calculate the global truncation error by summing the local truncation error of each interval for each step. So again, let us take n intervals. If we take the complete domain to be length L, step size h, we have n is L over h. Then we get our global truncation error to be equal to this local error O of h to the third times n, and therefore you will have a global error dependent on h squared. And if we compare it to Euler's method, we can see that Heun's method indeed improves the accuracy of the approximation. It reduces the truncation error, because we saw for Euler's method the local truncation error depended on h squared and the global error on h. So how do we implement Heun's method? How do we apply it to problems? So we can implement it using a predictor-corrector approach. So recall that in Euler's method, we estimated the slope at the beginning of the interval. So this is yi prime. And we use that to predict the value of y at some point further along in the interval. And that is depicted here in this equation. We have y at I plus 1 is going to be equal to yi plus this derivative of y at I times the step size h. And now we use a superscript of 0 to indicate that this is a predictor of the value of yi plus 1. So we call this a predictor equation. And now we use that estimated value of yi plus 1 to estimate or to calculate an estimate of the slope at this point, at the end of the interval. So that is given here. The derivative of y at I plus 1 is going to be the function evaluated at these points. And then we can average out those two slopes to obtain an average slope that is given in this expression. And if we plot that back into Euler's method, so we have this as the average slope times the step size, and then we get this final expression of Heun's method. So we have these two equations for Heun's method, predictor and a corrector equation, that we use to implement the method. So now let us discuss an example. So consider the following ordinary differential equation, namely this function, and it's an initial value problem, so we are given the value of y at x is 0, and it's going to be equal to -5. And now we want to solve this differential equation numerically, so using Heun's method, we want to find a solution for y, and we want to find it over the domain of x ranging from 0 to 5, and we will use step size h is 0.1. Okay. So we have this function of f, and with these values of y0, x0, and h. And now we want to use the predictor and the corrector equations. So we can find y1, the predictor of the value of y at one step size away. Recall that this is equal to y naught plus this function, so that y naught and y, or x naught and y naught, times this step size h. This is just Euler's method, basically. And here we can plug in the values that we have, our initial values. So y naught is -5. Then we can plug in the values for our function. So x naught is 0. Again, -5 squared plus 2 times -5 times the step size h, 0.1. And now we can just calculate this. It's going to be equal to -5 minus 10 times 0.1. So it's going to be equal to -6. So this is the predicted value of y1. Now we're going to use this value to estimate the slope and then to correct this estimate. So we have this corrector equation that is y1 is equal to y naught plus this function f of x naught y naught plus f evaluated at x1 and this estimated value of y1. So these are the two slopes that we average out. And now we divide it by 2 times the step size again. And we can plug in the values to get -5 plus -10 plus, and we plug in the values of x1 and y1 into this function, so we get 0.1. Oh, okay. Okay, hello. Yes. 0.1, which is x1, times y1, so we have -6 squared plus 2 times -6 divided by 2 times 0.1. And then we can just calculate this, and we have -5 minus c minus 10 minus 18.4 over 2 times 0.1, and the final answer is going to be -5 minus 0.92. So this is our final obtained approximation of y1. And we can continue this process to find, yes, okay, so these were the predictor-corrector equations. We obtained these values for the predictor and the corrector. And we can continue this process iteratively, so we would calculate y2 from y1 and so forth. Then we, if we do this in MATLAB, we obtain the following table of values of y and x. And if we plot them, we get this graph, where the blue plot is the exact solution to the differential equation, and the black dots are the values that are obtained using Heun's method with step size 0.1.